Good morning, everyone. Welcome to the seminar. We have a visitor these days here, Carlos Badenes. Carlos is assistant professor in Pittsburgh University, and he's enjoying a sabbatical year now in Barcelona, where he's from, and and now we took advantage of him being nearby to bring him here and tell us about his recent work. He did his PhD around 2004, right, at the Polytechnic of Catalonia, and then was a postdoc researcher in Israel, also in the US at Princeton and in Rutgers University, and now he's been for some years in Pittsburgh. His main interests are Type Ia Supernova, supernova remnants, and also the progenitors of those supernova, close binary systems with white dwarfs that are created. And in the last few years, he's been focused a lot on taking advantage of this generation of spectroscopic surveys, massive spectroscopic surveys like Sloan, APOGEE. In the future, it will be WEAF, DESI, and others, to study the populations of binaries. And well, I think that's what he's going to talk about today. Please, welcome.
So, thank you very much. I want to give a big thank you to Carlos for inviting me to come here. We should get this started like this. And there we go. Okay. So yeah, today I'm going to talk about stellar multiplicity in general, and how to use this new generation of astronomical surveys to do more about this. So of course, this work that I do with my group at the University of Pittsburgh, and there are many people here. Not all of them are working on this topic, but I would like to point out my student Christine Mazzola, who just started her PhD with me, and she has been an integral part of this work. So I'd like to start with an image. This is an image you're probably all familiar with. I've been a fan of Star Wars for many years, and like many fans of Star Wars, I've cursed George Lucas, right, for the second trilogy. Now, whatever you think of George Lucas, you have to give him credit for planting this image in the brain of everyone. Okay, this image is from 1977. That's 20 years before the first exoplanet was discovered, and 30 years before the first circumbinary exoplanet was discovered. And this image is absolutely correct. We know there are systems like this, orbiting an inner type binary. Okay, and actually in the literature, these systems are called Tatooines. It's a little homage to this image, right? So today I'm going to talk about closed binary systems, why those systems are interesting to us, and what questions are left to be answered in this field of research. I'll talk about the radial velocities from large spectroscopic surveys as a new source of data that can bear into this question and help us learn things about this. And then I'll discuss a little bit two different kinds of results on white dwarf binaries, and then multiplicity statistics versus stellar evolution and metallicity in the APOGEE survey within Sloan Digital Sky Survey. And then I'll end with some conclusions and implications. So let's begin with a little bit of an introduction. Now, a very simple working definition of a closed binary is just a system that will interact at some point, right? Binaries that are close enough that they will not evolve as separate stars. And of course, the image, I showed you the image from Star Wars. That's a powerful image. This is another very powerful image. We all have this image in our brain. What we expect is that at some point one of the stars will evolve off the main sequence, increase its size. If it has a short period binary companion, there will be Rochelov overflow, mass transfer through the inner Lagrangian point. You will form an accretion disk because you need to get rid of angular momentum, and something interesting will happen to this star. Right? This is all from all the astronomy textbooks that we know and love. However, no one has ever seen this in real life, because these systems are very, very small. This is about the size of the inner solar system. And of course, they're far away, so you cannot resolve them. So this image is a construct that's in our brain, and it's a very well physically grounded construct, but it's still a construct. And we have to be very careful and always look at the systems with some measure of healthy skepticism. Because there may be ideas in our head that are not born by physics. Of course, the reason we're interested in the systems is because they make all sorts of fun stuff, right? This is an image of Myra A plus B, a particular nearby binary, and you may be fooled into thinking that this is an image of something like this, but that's not the case, because Myra is far too wide. What you're seeing here is not the one of the stars. The star is like buried in here. This star has a wind, and there's some kind of mass transfer that goes through wind here, but it's not that. Okay? We've never seen this. Now with ALMA, we're beginning to be able to resolve things, and we do see that around Myra B there is some kind of extended structure that you may want to call an accretion disk. Okay? But I have to insist, we've never seen something like this in reality. Right? Now these systems are going to make all sorts of interesting things unless you've been living in a cave. You know that gravitational waves have been detected, yay. And now we have not only gravitational wave sources, but gravitational wave sources with electromagnetic counterparts. Right? Now, well, these are binary black holes and neutron stars, and they all come from closed binary systems, like the ones that we're discussing here. There's, of course, Type Ia Supernovae. Those come from closed binary systems, too. And there's all sorts of interesting objects in astronomy that come from binary systems. And this is a little quiz that I did for the people at the University of Barcelona, where they had to name the source. Right? I'm going to spare you that. These are the names. Supernova 1987A, that's a core collapse supernova, but it had a binary progenitor. That is how you form this three-ring structure. This is a very famous variable, the 838 Mon, that had a light echo that also comes from a closed binary system. This is ESO SPY, a white dwarf binary recurrent nova in our galaxy, also a binary system. And this is SS433, a microquasar, all closed binary systems. Okay, so this is, of course, intelligent, incredibly important, and it's important for us too to approach this in a way as systematic as possible. Last but not least, remember that image of Tatooine that I showed, right? Stellar multiplicity can also influence planet habitability, because planets that are in multiple star systems, and multiple star systems are not the exception, they're the norm. Planets in multiple star systems can have different orbital configurations. They can either orbit an inner tight binary or orbit one of the components, while the other component orbits separately. So Tatooine would be a p-type system. But the important thing about this is that when we think of planet habitability, usually we just think about radiation. We talk about the habitable zone as the range of orbits where liquid water can exist. Now, if you're in a multiple system, to this you have to add stability, right? Because you may have an orbit where water can be found in liquid form, but this orbit is not stable because of the configuration of the binary system. So this is also something that you need to take into account, right? If you want to put down the famous Drake equation, you need to know how many multiple stars you have and what the period distribution is. Otherwise, you don't know which of those may be stable or not. But if you're in an unstable orbit, the planet plunges into the star, that's very bad for life. Okay? You don't want that to happen. So the way we study this systematically is through what we call the statistics of stellar multiplicity. And these are just functions that we calculate in some way, right? These are basically one number and three distributions. The number is the multiplicity fraction, number of stars that are in multiple systems, and then the three distributions are the distributions of periods, mass ratios, and eccentricities. Now, if we can measure all of these things perfectly, we know everything we need to know about stellar multiplicity. But of course, we can't measure these things perfectly, and it's really, really hard. Actually, we've only measured this to a decent degree of accuracy for solar-type dwarf stars in the solar neighborhood. That is, stars that are 25 parsecs or closer to the sun. Outside of this, we don't know. We know some things. We know the multiplicity fraction is a very strong function of primary mass. We know that more massive stars tend to be in multiple systems more often. For stars that are about a solar mass, multiplicity fraction is around 0.5. But for stars that are core collapse supernova progenitor, practically all of them are in multiple systems. The period distribution for sun-like stars in the solar neighborhood looks like this. This is a distribution that we'll call log normal because it's normal in the logarithm. This is the logarithm of p in days. And what you have here is that there are systems with very short periods. This would be close to Tatooine, right? The systems are separated by just a few times the solar radius. But they're in the main sequence, so there's no Rogelov overflow. That period for a sun-like star would be of the order of less than a day. And then you can have longer and longer periods. Longer and longer periods are more and more common. The most common periods are around log p of 5, 10 to the 5 days. And then the question you want to ask is which of these systems are going to interact? Which of them will have some kind of mass transfer between the components at some point in their evolution? And that is this range here. So we are interested in the short period tail of this distribution. All this here, this is fascinating, but this does nothing to stellar evolution. These are stars that will evolve separately, and they are gravitationally bound, but they are not going to transfer mass. So we're interested in these guys. Log p of minus 0.35 to log p of 3, let's say. These are the systems that make all the fun stuff that I showed you. The mass ratio distribution, and again, this is for sun-like stars in the solar neighborhood, is approximately flat. I don't have a picture of a flat distribution because flat distributions are boring. But you can also see the eccentricity distribution, and you see that short period systems tend to be circularized because of tidal interactions. And as you go to longer and longer periods, the maximum eccentricity gets larger and larger. This is what's called a thermal distribution of eccentricities, and we think that's what's going on, right? Now, one problem with these numbers and functions is that they're not independent from each other. Okay? So, for instance, this is a plot from a very, very nice paper by Maximo and Rosanne Di Stefano, where they actually reviewed all the evidence for this. If you look at the distribution of periods and the distribution of mass ratios, these are not independent of each other for different primary masses. What that means in practice is that you need very large samples of multiple systems in order to explore all these interdependencies. You can't assume that you can measure one thing and measure another thing, and these two things are going to be independent. So already at the beginning of the talk, we're getting into the very complicated level of things. Okay? So let's scale back and do some very naive physical expectations. That's always good and informative, right? From the point of view of physics, Rogelov overflow is a very simple process. You have two systems. There is a point at which the gravitational pull from one component and the gravitational pull for the other component is exactly the same. If the size of one of the stars gets to this point, you know something interesting is going to happen. This is what we call Rogelov overflow. So the period for Rogelov overflow can be written down like that. This is for equal mass ratio systems. If the mass ratios are different, you're going to have a slightly longer period, but that's the smallest critical period for Rogelov overflow that you can have. And this depends, of course, on mass and depends on radius. Now, until you get to the AGB phase, a sun-like star really doesn't lose a lot of mass, so this is essentially a function of radius. And we know the radius of stars increases a lot once you leave the main sequence, because that's why red giants are called giants. They are very large, right? So if the radius increases, the critical period is going to increase, And what's going to happen is that a system, for instance, that was living here, everything is fine while you're in the main sequence, but when the primary hits the red giant phase, at one point this is going to have a critical period that's going to be shorter than its actual period, and therefore mass transfer is going to happen. Okay. As I was saying, this critical period is -3.5 log p of days in the main sequence, and gets to log p of 3 at the tip of the red giant branch and 3.4 at the tip of the AGB. Now, if you put this in terms of radius in a stellar evolution model, just to know what you're talking about, right? You have, this is time, this is the log of the radius of the star, this is for a sun-like star with mesa. You have what we call case A mass transfer, which is when you have mass transfer in the main sequence. This can happen because the radius of the star increases a little bit in the main sequence, but not very much. By and large, the most frequent type of mass transfer is what we call case B mass transfer, which is mass transfer during the red giant phase. In theory, you can also have mass transfer during the AGB phase, after you start burning helium at the core, but that's actually a lot less frequent because most of the radius change happens in the red giant branch. Of course, you can't measure the radii of stars directly, but you can measure log G, the effective gravity. So for main sequence stars, you're talking about effective gravity of 4.5. And then from 4.5 to say 0, there would be the red giant branch. And these are things, this is something you can actually measure from the spectrum. Interestingly, after you ignite helium in the core, the star will shrink again. It will become a red clump star. And here it could conceivably have short period companions, but in reality it shouldn't have any, because all the short period companions will have been removed during this phase. So this is kind of something that you expect. It has never been seen with a large sample, but you expect. Now, what happens when mass transfer starts? That's actually a very interesting question. It turns out that in many cases, not in all cases, but in many cases, this mass transfer is unstable. And something like this should happen. This is what we call a common envelope episode. And basically, what happens here is that the outer layers of the primary are being shredded by the secondary. And this is a fascinating problem from the point of view of physics, but one that's very, very hard to simulate accurately because there are many different scales involved, and this is actually unsolved at this point. We know there is a possibility of losing a lot of angular momentum in an episode like this, and that would make the orbit shrink. But this is not something that we understand from first principles. We think there may be observational counterparts to this common envelope phase, and this image that many of you may have seen from VA38 from Hubble Space Telescope may be an observational counterpart of one of these common envelope episodes. Okay? Good, so what are the open questions, and this is sort of the end of the introduction. What are the open questions in this stellar multiplicity? I hope I have convinced you this is an important problem, but there are many, many things that we still don't know. So multiplicity statistics, multiplicity fraction and the three distributions, period, mass ratio, and eccentricity, are only known accurately at all periods in the main sequence and in the solar neighborhood. And that's it. Outside, we don't know. We know some things, but our knowledge is very partial. There are some studies in stellar clusters. Stellar clusters are wonderful because you have a lot of stars in one place, so you can get a lot of observations of them. But they don't tell you much of the field population. And we know that the vast majority of the mass of stars in the Milky Way are in the field, not in clusters. As of no panoramic view of the interplay between multiplicity and the main properties of stars, age, and metallicity in the Milky Way. What do we want to know? Very basic things. Are basic ideas about Roche-Lobe overflow correct? Is this image we have in our head that we use to interpret so many of the things we see in astronomy basically correct? Does age or metallicity influence stellar multiplicity? Are stars of different metallicity equally likely to be in multiple systems? Or is this something that changes? Because if it changes, then the rate of gravitational wave sources changes. The rate of Type Ia supernovae changes. The rate of core collapse supernovae changes, and all sorts of things can happen. Right? Is there a connection to star formation theory? Star formation theory is another aspect that is not well understood, not from first principles, because it's very, very complicated. But people who run those models sometimes say, well, metallicity or environment should influence the way stars are formed and the way multiple star systems are formed. Is this true or not? And finally, what is the rate of common envelope events in the Milky Way? How often does something like this happen? Okay, sometimes we see it, but a lot of episodes like these are not going to be seen. And this is crucial because this influences the rate of stellar mergers, the formation rate of short period systems, and supernovae gravitational sources, etc., etc. So it is important to have systematic knowledge of these things in order to get a handle on rates and be able to understand the specific individual objects that are so interesting. Okay, so what new data do we have that can be useful for this? Well, of course, there's surveys, and surveys are wonderful. You have a lot of people here working on surveys, so I'm not going to, sell you a motorbike, as we say in Spanish. But the number of spectra of stars has been increasing, and it will continually and steadily increase. We have many, many surveys that have produced hundreds of thousands or millions of stellar spectra. Surveys like SEGUE or RAVE or APOGEE, WEAVE, LAMOST. This is not a complete list, right? So the wonderful thing about this is that you have a lot of data, and thanks to hardworking people like Carlos, these spectra are all very well characterized because someone has put in a lot of work to build a pipeline to measure effective temperatures and effective gravities and all sorts of things and metallicities so that we know what the spectra correspond to. A wonderful thing is that many of these surveys take more than one spectrum of stars for many, many different reasons, but they do. Now, there is one problem. The problem is that if you want to study multiple systems, this is the traditional way of doing it. You take one star, you take a lot of spectra, like 20 or 25 spectra, and you fit an orbit, right? And then you know everything. You know the period, you know the eccentricity. If you can solve for the mass function, you know the mass ratio. If not, you can at least put some constraints on it. But you never have this many data with surveys because surveys want to take data as many stars as possible. They're not going to repeat observations 20, 30 times. That's not going to happen. What you have in these surveys is 2, 3, maybe 4 radial velocities. And that's it. Now, radial velocities are great because radial velocities allow us to probe unresolved systems, and those unresolved systems are the ones that are going to interact. Log P of 4 or less is what radial velocity measurement gives you, and we want to go to at least log P of 3 in order to get the interacting system. So this is a wonderful way to probe this. But you don't have orbits. So what do you do without an orbit? And this is where I had an idea. This is me having an idea, and the idea is something that I had in conversations with Dan Malz in Israel a few years ago. We do not need to fit the orbits to answer many of the open questions about stellar multiplicity. And I'll show you how to do that. Now, is this a good idea? Well, I don't know. Okay. We'll see. So how does this work? Let's start with white dwarfs. White dwarfs are wonderful because they're small. If you calculate the critical period for a Rorschach overflow in a white dwarf and you work out the radial velocity shift that you expect between spectra, you get very large velocities, hundreds of kilometers a second. And this means even with low resolution spectra, you should see something, right? This is a white dwarf, spectrum of a white dwarf, observed with Sloan. And this is not a simulation, this is actual data. This particular white dwarf was observed 5 times with Sloan, the Sloan spectrograph. This is an optical spectrum. And you can see with your eye that the lines are moving. There is a large radial velocity shift. This white dwarf has a binary companion. Now, what is the orbit? I can't tell you. Well, I can tell you now because this white dwarf has been followed, right? But you don't know from this data. But you can measure the maximum radial velocity shift for this one object. Now, for that one object, it doesn't tell you much. But the statistical distribution of maximum radial velocity shifts in all the objects that you observe, if you observe enough, can actually tell you a lot. This is a histogram of number of white dwarfs here and radial velocity shift in Sloan. And you don't see here anything surprising. There are a lot of white dwarfs with very small radial velocity shifts, and a few white dwarfs have large radial velocity shifts. Like this one I showed you is this guy here. Radial velocity shift for around 400 kilometers a second. Now, if you had no white dwarf binaries in Sloan, and you observed 4,000 of them, you would expect to see this dashed curve, because you're going to have radial velocity measurement errors, and some of those errors are going to be large, and in a large sample you're going to have 2 and 3 sigma and 4 sigma deviations. But that's what you would expect. Now, anything above that curve is a statistically significant detection of binarity. And the shape of that tail depends on the number of white dwarfs that have binary companions and the period distribution. And you can run models for this, and these are these color lines where you vary the binary fraction and this alpha parameter. It's not important what it is, it's just a way to parameterize the period distribution, right? And you can see that your data are constraining the models in a certain way. If you see this, there are certain values of the multiplicity fraction and period distribution that are ruled out by the data. And you haven't measured the periods of any system. You just have the data that you have. Okay? Sure. The degeneracy between the distribution of periods and the oh yeah, so goes into this parameterization of the period distribution. You have to assume some kind of function. And in this case, what we have assumed is that it's just a power law, because you're actually not sensitive to the entire distribution of periods. You're just sensitive to the short period tail, because those are the ones that are going to give you radial velocity shifts. The longer period systems you can't measure, but you don't want to, because those are not going to interact. So you are sensitive with this technique exactly to what you're interested in. And as long as you have the capacity to parameterize that, you're going to be able to say something interesting about the entire population. And then, of course, if you're interested in that particular system, then you go to a telescope and follow it up, and then you get the period, right? And that's also a way to check. You can go back with all the systems whose periods you have measured, and you can know that that you did things right, and that you're within the parameters that you wanted to measure. Now, this is work that I've been doing for some time, and there's been a recent paper now combining the Sloan measurements, which is what I showed to you here, with measurements from a survey that was done in ESO called the SPY survey, where they took repeat spectra of white dwarfs with very, very high resolution using the VLT. And we're combining this now to get very strong constraints on the binary fraction and period distribution of binary white dwarfs. Now, why is this important? Well, this is important because binary white dwarf mergers are one of the leading models for Type Ia supernovae, for instance. And before we did this work, nobody knew if you really had enough binary white dwarfs to explain the Type Ia supernova rate. Now, if you constrain the period distribution and the binary fraction, the rate at which systems are going to merge is completely determined, because those are detached systems that emit gravitational waves, and you can calculate the rate at which the orbit is going to decay. So you can compare this to the Type Ia supernova rate. You here have a merger rate per star. You can compare it to the Type Ia supernova rate, and you see that you have more than enough. Even if not all merging white dwarfs give you Type Ia supernovae, you can reproduce the Type Ia supernova rate using just merging white dwarfs. This does not mean that all Type Ia supernovae are merging white dwarfs. Okay, but they could be. Another thing why this is interesting. Now, of course, you've heard about gravitational waves. The next generation of gravitational wave detectors are space interferometers, like the LISA mission of the European Space Agency. If you go to LISA, you know, this is LIGO, this is where we are now. LISA is lower frequency. You will see that the sensitivity of space interferometer like LISA depends on the noise level from unresolved white dwarf binaries, because these are the most common gravitational wave emitting sources in the Milky Way. So if you know the multiplicity fraction in the peer distribution, you can calculate this noise level, and this is a requisite in order to know whether LISA is going to be able to see a given source or not. So even if you don't care about supernovae, this is an important measurement to make. Okay? So more things. Can you do this for stars that are on white dwarfs? White dwarfs, as I was saying, are easy because they're very small, they can be very close by, and the radial velocity shift can be very, very large. But if you have good enough data, you can measure radial velocity shifts that are a lot smaller than 100 kilometers per second. And one of these surveys that has made this kind of work possible is APOGEE. Now you have Carlos here, so I'm not going to talk a lot about APOGEE because he's the real expert. But basically, this is just a multi-epoch infrared survey with a spectral resolution of around 20,000. That's observing hundreds of thousands of stars in the Milky Way at high signal to noise in the infrared. Right? And the typical APOGEE spectrum looks like this. And this is not noise. These are all lines. A forest of lines that are very sharp because these are pretty large stars, so the log G is pretty small. This is ideal data to do radial velocity work, because if you shift the spectrum by a little bit, you're going to see radial velocity shift very, very well. Okay, so APOGEE is looking at main sequence, red giant, and red clump stars. Most of them at about 1 solar mass, so these are stars that are very much like the sun. And it reaches most of the Milky Way disk because it's observing in the infrared, so it doesn't have to deal with dust so much. So you can see things that are really tens of kiloparsecs away, easily. And this is great because you really are probing all sorts of environments and metallicities, which is the kind of thing that we're interested in. Now, APOGEE has this wonderful pipeline that Carlos is responsible for. Well, no, not only him, but he has been the leading. And it measures effective temperatures, log Gs, metallicities, radial velocities, well, pipeline, but it's part of the measurement. And you can also use this data to identify red clump stars, which is something that you can do because they live in different parts of the parameter space. There's also a data-based code called the Canon that does very similar work, but it needs a training set, so it's important to have both. But anyway, you have a lot of stars measured with high precision. You can measure radial velocities very well, and you have many, many of them. So this seems like an interesting thing to try the stellar multiplicity statistics game. Okay, this is a Hertzsprung-Russell diagram of the APOGEE stars. You see that you have some main sequence here, and basically the red giant, almost all the way to the tip of the red giant branch, a log G of 0, and you can also see the red clump stars here. And this is what a 1 solar mass star would do along its evolution. Now, what would it look like this is the distribution of visits and the distribution of epochs, which is important if you want to measure radial velocity shifts. As you can see, you only have enough radial velocities to calculate an orbit for a very small number of stars. For the vast majority, you have 2, 3, 4 measurements that you cannot calculate an orbit, but you can play the game that I show you with the white dwarfs. This is what typical data for an APOGEE binary looks like. You have 3 spectra. You can calculate an orbit, but you see clearly that the lines are moving. You don't need to do sophisticated analysis here to see that the lines are moving. This system, this star, has a binary companion. Just to give you an idea, this is a radial velocity shift of 100 kilometers a second. This is a radial velocity shift of around 10 kilometers a second. And you can measure much, much more than that with APOGEE. So what happens if you, for instance, plot the effective gravity, the log G of the stars, against radial velocity shift. You get a plot that looks like this. This is effective gravity from the APOGEE pipeline. So the sun and dwarf stars are here, high effective gravity, and the stars at the tip of the red giant branch are here, low effective gravity. And you see that the maximum radial velocity shift that you can find in a star is a very strong function of its physical size. Not surprising, but very nice to see with a large sample. There are 100,000 stars in that plot. Now, if you take those expressions I gave you for the Rorschach overflow period, you can see that they end up like that. So this is theoretically the maximum radial velocity shift that you would expect to see for stars of different masses, and you see that it lines up with the data quite well. There are no systems to the right of this plot, which is good. These are histograms of different log-G samples. You can see how from the main sequence to the tip of the red giant branch, you basically are eroding the radial velocity shift distribution. This is the maximum radial velocity shift between two observations of the same star. You're eroding this all the way, and you have that the maximum radial velocity shift that you see is lower, and also that the number of systems at all radial velocity shifts goes down. And this is because you're removing the short period systems in a very efficient way from the population. Very interesting. If you look at stars at the tip of the red giant branch, these stars over here, and you look at the red clump stars, which are highlighted here, you see that the radial velocity shift distribution is practically the same. Even though these are stars that have physical sizes that are very different. Stars at the tip of the red giant branch have several hundred solar radii. Stars in the red clump have radii typically of 10 solar radii. Yet the radial velocity shifts are the same because those stars in the red clump, remember, they used to be larger, and they don't have any short period companions. They have removed them all during case B mass transfer. Remember that we're comparing these stars with these stars, and they have the same distribution of companions. So that's interesting. You can, of course, measure the number of systems with certain radial velocity shift as a function of log G, and you can run models for this. I'm not going to go into the details of this, but essentially what's happening is that you have this log normal period distribution. You are removing systems of longer and longer periods, and what happens is that in the main sequence you expect a radial velocity shift distribution that's like this. At the tip of the red giant branch you expect it to be like this because all the short period systems are gone. Right, so you can compare your models to the observations in this way, and this is how you get measurements of the multiplicity fraction and parameterizations of the period distribution, right? And you can see that at least in the red giant branch, the models and the observations line up very well. The main sequence gets complicated because the main sequence stars in APOGEE are probably not all of them around 1 solar mass, so I'm not going to go into the details of that, right? One more thing that I want to show you before I go into the conclusions is this allows us, of course, to study things like the correlation between stellar multiplicity and the fundamental properties of stars. One very simple thing to look at is what happens to stars of different metallicity. Do they have the same number of binary companions or not? Do they have the same distribution of binary periods or not? Now, if you take the APOGEE sample and you divide things in metallicity terciles, which means, you know, every log G range, you divide into a low metallicity, a high metallicity, and a medium metallicity population, you see this, right? This is, as a function of log G, this delta RV max histograms that I've been showing you. So this is the main sequence. You're going to larger and larger stars until you get to the tip of the red giant branch. This is the red clump. Forget about the red clump for a minute. But in all the other histograms, you see clearly, and this is a logarithmic plot. It's a log-log plot. So the difference between this and that is very large. You see the low metallicity stars are always above the high metallicity stars at all log Gs. Okay, and this is a very important realization. This means that low metallicity stars are more likely to be in multiple systems and to have short period companions than high metallicity stars. And this means that in a low metallicity population, all other things being equal, you expect more Type Ia supernovae, more gravitational wave sources, more of all the fun stuff that I showed you at the beginning of the talk, just because you have more binaries per star, right? And this is a pretty large effect. It's a factor of 2 or 3. Again, I'm not going to go into the details, just to give you an idea. This is the number of high delta RV max systems that you measure in the low metallicity versus the high metallicity. This is what you would expect if there was no effect, and this is clearly above at all systems. This is a measurement or an idea of what the statistical uncertainties are involved in this measurement. So this is clearly above any statistics. It is a real effect. And it's only because we have such a large number of systems that we have been able to measure. And this is just the surface. We've only started doing this work. Okay? So what are some of the implications? And here I end. I'll take 5 more minutes and then I'm smack on the 50-minute mark. Okay, so what are some of the implications? Now, essentially what we've done, we have measured the rate of case B mass transfer in the Milky Way. We've seen how many stars lose their binary companions as they climb up the red giant branch, right? And this is great because there's only one step from that. I'm not saying it's an easy step. It's only one step for that, and we're working on it to measure the rate of common envelope events and stellar mergers. And now, some of these new surveys that are looking for new transients, things like the Palomar Transient Factory or Pan-STARRS, though Pan-STARRS hasn't been as successful as that, they've started identifying this new class of variables called luminous red novae. These luminous red novae are systems that look like B838Mon. There's a star that suddenly gets very, very bright and then fades out. It's not a supernova explosion, it's not bright enough, but something interesting is happening to this star. And we think the common envelope events may be related to these. Now, there's an observation of this particular star. If you're not familiar with this, I don't blame you because this was published by an obscure group, but I think this is such a great observation. This is B1309 SCO, which is kind of a low mass cousin of B838Mon. Now, in that particular system, there was photometric variability before the nova. This is the nova, clearly. But here, the photometric variability allowed people to measure the period of the system before the nova. And they saw how the period was shrinking. So this was direct evidence that this kind of event comes from a stellar merger of some kind. The period shrinks, then the system gets very bright. Okay? And these are the kind of systems that could be the counterparts of common envelope events. And this is a key piece in our picture of all these things in the galaxy. It's a key piece. This is the key black box in all binary population synthesis calculations because we do not know how common envelope evolution works. But if we can measure the before and the after, there's hope that we may be able to get physics out of it. Okay? So this is kind of a BA38Mon. Now, the fact that you have more closed binaries at a low metallicity actually lines very well with some, but not all, star formation models. So there is a group in Japan, led by Machida and collaborators. They have run star formation simulations at varying metallicities, and this is kind of a complicated plot, but I just want to point out to you that systems with lower metallicity tend to have more companions at short periods, and there's more of them. So these people were very excited about our results. Yes, we were right. Now, maybe, okay? I'm not drawing a direct connection to star formation, but this is one of the things that could be going on to explain what we see. Okay, as I was mentioning, binary population system models in different environments will give you different answers if metallicity really plays a part, right? And this is crucial. It's the stellar evolutions, stellar astrophysics community. It's kind of fun to poke at the people doing binary population synthesis because they are dealing with these very complicated models that have lots of knobs to turn. These models are crucial. They are the only way to understand the rates of Type Ia Supernovae and gravitational wave sources. Right? These people don't deserve being poked fun at. They deserve all the help that we can give them, and this is kind of an attempt to do that. Right? And of course, this is important because the rate at which stars are formed in different galaxies is also a very strong function of metallicity. In other words, there are star-forming galaxies that have a very wide range of metallicities, and if this effect is true for their multiple stellar components, then you should see some kind of variation that is systematic. Another thing that we've known for some time, we know that metal-rich stars, all other things being equal, are more likely to host planets, right? But what happens for the habitability of those planets? What if the star is in a multiple system? Then if the star has a lower metallicity, it's going to be more likely to be in a multiple system, and the habitability of the planets is going to be jeopardized by this, because you have to satisfy an orbital stability argument besides a radiation argument. Right? So there may be a no-go zone in metallicity where the chances of forming a planetary system and those planets having stable orbits are actually very, very small. Right? It would be like a radiation field around metal-poor stars for life. Right? We don't know if that is true, but it's one possibility. Right? And just to finish very quickly, one of the things that we're doing for follow-up of these systems is getting photometry with the Assassin survey in the US. And when you single out systems with short binary periods and get photometry from them, some of them show photometric variability. And this is wonderful because this gets you a period, which from the radial velocities measurements from APOGEE we can't get, right? And this is a wonderful way to single out systems that may have interesting companions, some things like neutron stars or black holes, right? So stay tuned for more of this. Of course, Gaia is going to be amazing in this field because it adds another component. Now we're going to have distances for many of these systems. And also photometry, though the photometry and the radial velocities for Gaia are not going to be released until later. Do I have a conclusion slide? I think I do. I may have removed it, but I'm going to leave it here, and I'll take questions if you have any. Thank you very much. Thanks for your attention.
Well, thank you for the very exciting talk. I saw that you had a slide about WIV predictions, so
yes.
Could you go through that?
Sure. So I remember you were at the WIV meeting in Barcelona, right? Okay, so of course this kind of techniques, where do I have the WIV slide? This is Gaia. This is Gaia. APOGEE. This is what you may hope to see with WIV. So this kind of method is something you can apply to any large survey with repeat observations. Of course, we've done it to APOGEE first because it's kind of the first one that had a very large sample. But in principle, you could do this in the optical. You could do it with any other survey. You just need to be able to measure the radial velocity shifts. Right? So when you're planning your survey, like the WIV people are doing now, you may want to ask yourself, what is the survey strategy that maximizes the stellar multiplicity science that I can do with this? And the key thing here to remember is that in order to do stellar multiplicity science, you do not need orbits. You just need lots of radial velocity shifts. Right? So these are simulations that I run on what happens when you have, for instance, the top right panel is two observations with a lag between them that's uniformly distributed between 1 and 90 days. So if you have the privilege to take just two spectra of each star, and you can do this within the same observing season, you can get a lot of binary science. Right? Now, what happens if you can only take spectra back to back? If you can only take spectra back to back, then you're going to lose a lot of the binary science, especially for large stars. This is for different log Gs, right? But in principle, you can do this at no great cost to the survey, adding a completely new dimension to the science that you can look at. Most of these surveys, like APOGEE, they're not built for stellar multiplicity. They're built for galactic archaeology. And that's great, but you can do both, right? Because what I showed you is really a good combination of stellar multiplicity and galactic archaeology. It turns out metallicity has an impact on stellar multiplicity. Metallicity has an impact, also will stellar age, right? Because they're tied together. So this is the sort of thing. And when you're planning the survey, this is really something you should take into account. Of course, you don't want to compromise the goals of the survey by taking many, many spectra of every star, but you don't have to do that in order to do interesting science.
Well, I guess as long as the observations will not be done back to back, this will be this output will come for free, at least in the high resolution mode for the
Exactly.
galactic archaeology survey. Because it's anyway planned 2 observations
Yep.
per exposure. And then I have another very short question.
Sure.
Is I think the work in trying to see how the distributions vary as a function of log G is very nice. And I mean, obviously the stellar parameters pipeline will have errors attached to that.
They all do.
And I was wondering what kind of precisions and accuracies are very important for this
Okay,
kind
so
of
that's a
work.
very good question. For this particular work, we were comparing stars sort of across the stellar evolution stages that APOGEE is sensitive to, so from the main sequence to the red clump. In that case, relative accuracy is usually enough. As long as you can be sure that this group of stars have a lower effective gravity than that group of stars, you're going to be able to see the trends that you're interested in. Now, if you want to do more accurate measurements, and say, okay, well, this is the multiplicity fraction of stars in this log G range, then you're talking about absolute accuracies, and that gets more complicated. Okay? We're repeating now the work with DR14. What data I showed is DR13, and for the DR14, actually, this was Carlos's suggestion. We're using the calibrated values. This means that probably we won't be able to go all the way to the main sequence, but at least we will be able to see the systematics in the red giant branch much better. And we're hoping to do that in order to get actual multiplicity fractions, which is possible but not trivial. And this is what my student Christine is working at. So you do have to be careful when you're looking at the pipeline. And one thing, there's always more than one way of measuring these things. Like, for instance, you can compare the log Gs you get from the pipeline that APOGEE put together with the log Gs you get from the Canon, and that gives you a sense. But again, there's no free lunch, right? There's no perfect, absolutely robust way of measuring these things, and you have to be careful when you're making these comparisons, always. Yes, more questions?
Yeah. Regarding the point about the possible link with the metallicity, the numbers that you get as a function of metallicity, did you ever cross these numbers with the fact that the different lifetimes characteristic for every phase?
Yes.
Because this might be important because you are maybe sampling in a different, although the age might be the same.
Exactly.
The evolution.
Exactly. So
Have some impact.
So yeah, so all things being equal, when you change the metallicity of a star, you change its lifetime, mostly because you change the rate at which it will lose mass when it gets to the AGB phase. Now, this effect is not so large in the red giant branch because red giant branch stars are actually not losing mass that much. The really heavy mass loss comes in the AGB phase. But you're absolutely right. Everything is tied together, right? H, metallicities are all aspects of the same thing. The only reason we presented our results as a function of metallicity is because metallicity is relatively easy to measure from spectra, right? And it's relatively unambiguous. But now the interpretation of what we see and how the multiplicity fraction actually depends on things like environment and age. These are things that we haven't really begun to explore, right? Because you need a model that takes all these dependencies into account in order to make a statement about these things. At this stage, our work is very observational. It's very close to the observations, but of course the interpretation will need to take all these things into account.
It is, however, a very important result also for longer scales, like even galaxies, no? because I mean this might be possibly linked to the star formation theory.
Yes.
But the star formation, of course, it's also, I have tried to think whether I could find a link, and it's really difficult.
It is.
It's like counterbalancing aspects. It's very difficult to get an idea, a clear idea, by just thinking, no? And I think the problems with the star formation, if you want to rely on the star formation theory to get such a conclusion, is difficult because the time scales that where you can develop these models is not going to be longer than 10,000, maybe, I don't know, a bit more. For example, you mentioned the paper of Babe, okay, and these are limited to the first 10,000 years, or if you want to multiply by 10. Okay? So it's very difficult to follow. For example, depending on metallicity, the clumps, according to Babe, indeed, the clumps are larger for at lower metallicity than in high metallicity regime.
Yes. Yes. So that's what makes it interesting, right? Because
this seems to go in the opposite
in the opposite direction, exactly. But that's what this observation is interesting, I think, because if you look at the star formation theory, and I'm not an expert in this, but if you look at the star formation theory, you have kind of competing claims of effects in different directions. Like, for instance, Machida said, okay, well, lower metallicity systems should have more short period companions, and they said, well, I don't see in the metallicity ranges that we have explored, I don't actually see a big systematic effect, right? So I had an interesting conversation with Paulo Padoan, who's an expert in star formation in Barcelona. He told me, yeah, well, this is really interesting, but you need to run a lot of simulations to really explore this. Simulations that are already very taxing, right? These are people working at the edge of what computers can do now. And I'm sure we will see more work on this in the future, but it's exactly what you say. By the nature of the problem, you can't write down some simple equation of physics that will explain this, because you have many competing effects. So nobody really knows where the coin will fall, right? Now the fact that there is an effect from the observations is clear, but what this means is something that it's maybe going to take us time to.
And just a final comment.
Sure.
The implication might be also related to the possible variation of the M.
Oh yeah, well, of course, but that's always part of any of these things. Yeah.
Okay, just a very short question. In your model, how do you break the degeneracy between periods and mass ratio? Are you assuming equal mass binaries? Or?
No, we're not assuming equal mass binaries. What we're doing is we have Monte Carlo models where we keep some things fixed, and we vary some other things. And what we did for the mass fraction distribution in these Monte Carlo models is we took the mass fraction distribution that is observed for sun-like stars in the solar neighborhood, which is kind of flat in mass ratio. And that's how we derived our comparisons between models and observations. Now, we varied this within reason, and the results didn't change very much. But of course, if the mass ratio distribution in the field of the Milky Way is pathologically different from the mass ratio distribution in the solar neighborhood, then that's something that's kind of built into the interpretation. In this paper and in the work we're doing, we're trying to make very sharp distinctions between what the observations say and what the interpretation of the observations is. Now, of course, we're interested in the multiplicity fractions and the period distribution, but those are interpretations of observations, right? And when you're running these models, you're never completely invulnerable to systematic effects. So you have to be very careful with that.
Is there any other question? Yeah.
So a comment to your slide on the between RGB and red clump stars. You say it has not been observed. A couple of years ago, we did a study combining binaries and astrosseismology, and we found a highly overabundant ratio for red giant branch stars over the red clump stars, just accounting it to the common envelope phase.
What I said is it hadn't been observed with a large sample, but you know.
Okay, well, just want to mention, drop the word astrosseismology in here. Yeah. So That's probably
No, I think that's very interesting, and of course, and this is, comes within the constraints of giving a 50-minute talk about anything. The field of literature in stellar multiplicity is vast, right? And I'm kind of new to it, so I am aware that I probably missed many things. I think it's very interesting, for instance, to put together what we learn in the field from what we learn in clusters, which is kind of a completely different way of looking at the problem. But of course, the underlying physics should be very similar, with some exceptions, right? But yeah, I'd be interested in actually getting that reference to make sure that I mention it in the future.
Well, there is scientific coffee, I remind you, so maybe you can continue discussions there. And we thank Carlos again.
Thank you very much. Thanks to everyone who came.
Just to mention that Carlos will be here today and tomorrow morning in case anyone wants to talk to him. Stop by my office and send an email to me or him. Thank you.